So the last thing I needed to cover yesterday for running out of time was charges. So looking at a periodic table, the first column all has one valence electron. The second column all has two valence electrons on their outer shell or energy level. Skipping transition metals, these all have 3, these have 4, these have 5, these have 6, these have 7, and these have 8. The octet rule states that every atom wants to become stable by having a full valence shell. They want to have 8 electrons. So let's look at lithium. There is an exception to the octet rule. So the exception is the first energy level is 2. Everything, all other energy levels, so for example, hydrogen and helium are full if they get 2 electrons. Because the innermost energy level has at most 2. The rest of them can hold more. So here's the Bohr's diagram for lithium. So it wants to have a full outer shell. It has 1 valence electron. Now then, there are 2 ways it can achieve this. It can lose 1 electron, and then it'll be left. So if it gets rid of this electron, it will have the innermost shell full. Or it can gain 7 electrons, filling up this shell. Which do you think is easier or uses less energy to do? Lose 1 electron. And if you lose 1 electron, do you what would your charge be? Positive. So it'll get a positive plus 1 charge. So lithium becomes lithium plus ion. Let's look at phosphorus. So phosphorus, number 15. So writing the Bohr diagram for that. It's in the 3rd row, so it's going to have 3 energy levels. Yeah. And it has 5 on the outside. 1, 2. So it has 8 electrons, so writing out its full configuration. That's 1s2, 2s2, 2p6, 3s2, and it's in the 3rd spot in the p blocks, so that'd be 3p3. So for the 3rd energy level is 5, so counting them out, 1, 2, 3. For the 1st energy level, it has 2 electrons. For the 2nd energy level, it has 8. And for the 3rd, it has 5. So this is the Bohr model. And it wants to have a full shell, a full outer shell. So it can achieve this in 2 ways. The second energy level has 8. So it can lose 5 electrons. It can lose its outer shell, and the second energy level will become the new outer shell and be full. Or it can gain, how many? That's 5 currently. It can gain 3. 5 plus 3 gives you 8. And fill up the third energy level. Which do you think it would want to do? Gain 3. So, what would its charge be now? So it gains 3 negative electrons. So it's gaining 3 negative. So its charge is negative 3 charge. So when phosphorus becomes an ion, it becomes P3 negative. And if we look at the periodic table, so 1, it has 1 valence electron. Would these want to lose 1 or gain 7? And their charges would be plus 1. Would this want to lose? So you're either trying to reach 0, meaning throw away your outer shell, or fill it up by getting 8. You want to try to get a 0 or 8. So if you're closer to 0, you're going to lose them electrons. So all of these are going to be plus 2 charges. And what would all of the 1 in the boron group be? Plus 3. 3 is closer to 0, so it's going to lose the electrons and become positive. What about carbon group? Is 4 closer to 0 or 8? Right in the middle. Plus 4 or minus 4? It depends on what it's bonding with. It can do either or. These usually don't become ions. They're actually stable. They're perfectly in the middle. I mean, they're not too stable. They're perfectly in the middle, to which they can go either way to become more stable. So losing 4 takes about the same amount of energy as gaining 4. This is much easier to gain 3 electrons, so become minus 3. These more easy to gain 2 electrons, 2 negative electrons. This is going to have a charge of negative 1, and this is going to have a charge of 0. The ones in the carbon group kind of depend. And of course, there's always exceptions, but we won't worry about the exceptions. Most of the time, you won't encounter any major exceptions. What we end up having is there's going to be exceptions, like in lead. Lead is an exception. I think it's plus 4 or plus 2. It's really weird. That's because the heavier you get, some other things start going on. But we will ignore all exceptions. I won't give y'all any complicated examples. You just use these numbers. So there's the charges. Let's look at table salt. This is getting a little ahead of myself. But what is the charge of a sodium ion? First of all, does salt have a charge? It's neutral. It has no charges, right? if it had a charge, you would see it would immediately repel everything. It would repel itself. It would break up. Another salt molecule couldn't be next to it because two negative charges or two positive charges would repel. But the fact that they don't repel each other and we can have giant crystals of salt means no charge. This is neutral. This molecule, so table salt, sodium chloride, neutral. But let's look at sodium. What is the charge on sodium? So plus 1, or 1 plus, and again, we don't include the plus, 1. And what's the charge on chlorine? So minus 1. So what is plus 1 minus 1 equal to? 0. Now you know why table salt exists. Let's look at another common chemical. Yeah, I mean, like, this is going to be how we do reactions. It's literally, my point is showing you this. You need to have this down. You need to make sure you completely understand charges. Yes. So sodium is going to be plus 1. Later in the year, after Christmas break, we're going to do a lot of reactions. And you need to be able to say, let's see, calcium chloride, for example. So what's the charge on calcium? Not calcium, calcium. Ca. Positive, so plus 2. And what's the charge on chlorine? So this column. So 1 minus. Again, we usually don't include the 1. What do you think the formula is going to be when we combine these together? That's 7 valence electrons. The charge is minus 1. Is that what you're talking about? Oh, let's say, so I meant calcium and chlorine. I'm just making up two chemicals. So we have calcium and chlorine. What do you think they're going to be if they react together? What do you think the formula is going to be? So when we took sodium and chlorine, it produced a neutral stable atom with charge 0. And that's because plus 1 and minus 1 equals 0. So how would you count? So this has 2 plus, and this has 1 minus. So the formula is 2 chlorine atoms will bond to 1 calcium atom. So this has negative 1 charge, but there's 2 of them. So overall, this has a minus 2 charge. And this has a plus 2 charge, and there's 1 of them. So this has a plus 2. Plus 2 and minus 1 add up to 0 charge. So this is the chemical formula for calcium chloride. Again, we'll be doing this later in the year. Right now, you just need to get down on electron. This whole unit is just on electrons. So this is charge, and this is valence. So, and there's a section on helium. It has 2 valence. Really what you need to memorize is the valence. And then you can ask yourself, does 6 want to go to 8 or 0? Is it closer to 8 or is it closer to 0? Closer to 8, so we're going to add 2 electrons, and electrons have negative charges. Over here, magnesium has valence electron 2. Is it closer to 0 or 8? It's closer to 0. We need to remove negative charges, 2 of them, so that is a +2 charge. When you look at the homework I gave yesterday. Yes. Yes. What do you mean between 2 and 3? None of the homework problems give that. Like I said, there are exceptions to everything, so I'm not going to ask you about them because you have to know the exceptions. You actually have to memorize all, like, 50 exceptions. Basically, for the transition metals, you have to memorize their ion states, and they often don't have one. For example, iron. Iron can either be 2+ or 3+. Nope. Just randomly. Just randomly. These are the 2 types of iron ions. So iron oxide is wrong. You know what iron oxide is, right? Rust? This is wrong. It's actually iron 3 oxide. Because it's Fe2O3. Where Fe is the 3 plus ions, and O is the 2 negative ions. Again, this is advanced things, but saying iron oxide is horribly wrong, because this chemical here, iron 2 oxide, is a completely different chemical than iron 3 oxide. Yes. The valence electrons and charges, and yes, you have to memorize everything. So, for example, in the sodium, look, this one right here, lithium, it lose 1 electron to get the Li plus. Because it loses 1 electron rather than gain 7. The question asks how many electrons does it lose or how many does it gain. So look at phosphorus. Phosphorus gains 3. That's what you would write for phosphorus. We literally just did several examples. So this beryllium has 2 valence electrons. Would it rather lose 2 electrons to reach 0 or gain 6 to reach 8? You're trying to get a full shell, a full outer shell. You could either remove the current outer shell and end up with a lower shell that's full, or you can fill the outer shell up. That was the entire class of me explaining how to do it. Do you not understand this? So it tries to get a full shell. It can get a full shell is 8. So I can end up adding, so look at the outer shell. The outer shell has 5 on it. I can add 3 and have it full, or I can remove these and have a full shell now. So this would be the current shell. Whichever number is less is correct. Because this is easier to gain 3 than to lose 5. Cassidy, you're trying to walk to a gas station. One gas station is at the 0-mile marker. Another gas station is at the 8-mile marker. If you are at 6-mile marker, would you rather walk 2 miles to this gas station or walk 6 miles to this one? So, if you're doing this side you are gaining 2 miles to your mile marker, and your left is losing, so you're losing the 6 to get to the 0. Does that make more sense? So they're either trying to reach 0 electrons, that's removing the outer shell, or trying to fill it up by getting 8 electrons. Let's say it currently has 3 electrons. So it's either going to try to lose 3 or gain 5. And you have to ask yourself which is easier to do. It's easier to lose 3 to get to 0 than it is to gain 5 to reach 8. So when you gain, that makes it negative. And when you lose, that makes it a positive charge. So this is for charges. I think one thing also left off. Remember when you're writing Lewis dot diagram, so carbon has 4 valence electrons. You need to write it like this. If you look at oxygen has 6, so 1, 2, 3, 4, 5, 6. These pairs right here are called electron pairs. Again, this is more advanced for later in the year. If we look at water, I don't know if I said this yesterday. So water is H2O. Have y'all seen pictures of the water molecule? It's bent like this. Do you know why it's bent? Because one of these electrons is bonded with or shared with a hydrogen, and there's actually an invisible electron pairs right here, making it a perfect plus sign. We usually don't write the electron pairs in it, but that's the reason why a water molecule is shaped like this. Is because there is an invisible 2 electron pairs on the opposite sides, making it purely symmetrical. It depends. One of the questions, if it says write gain or lose, then you would say you gain 2. If it's asking about charge, then you would put minus 2. So if you gain 2 negative charges, you become more negative. Another way of looking at it is, let's do oxygen for a second. Oxygen has 8 protons and 8 electrons. And it has 6 valence electrons. In order to become more stable, the 6, it wants to gain 2 electrons. So that means it wants to become something that has 8 protons and 10 electrons, because it wants to gain 2. So this is negative, and this is positive charge. So plus 8 charge and minus 10 charge is negative 2. So gaining 2 electrons gives you a negative 2 charge. Yes. If it's on the 8, it does not gain or lose either. So put 0 gain or 0 loss, or none. You can write the word none. Or neither. Another thing about ions is, let's look at Li+. The Lewis dot for it, so the Lewis dot structure is Li. Let's look at O2 negative. So O2 negative now has a full valence electron, so the Lewis dot for it is going to be O with 8 dots. What you see is ions, either except for helium and hydrogen are exceptions. You see that positive ions, and technically, do this, I forgot this. You need to put it in brackets and put the charge on it. So positive ions are going to look like this, and negative ions are going to look like this. So the Lewis dot notation for ions is you put the Lewis dot for it and put brackets with a charge outside of it. Yeah. So nitrogen has 5 valence electrons. So when it becomes an ion, it's going to become N3 negative. So the Lewis dot for it, since it has 5 electrons, is going to look like this. But the ion version of it, so the ion version, is going to look like this. It gains 3 electrons, so now it has 8. And this would be the valence electron. Can I answer any questions about this homework? I could write over here too, lithium, whenever it becomes an ion, the lithium plus. And the Lewis dot structure for it would just be the single dot. And when it becomes a ion, the dot is removed, and you put brackets around it to indicate that this is indeed the ion version of it. noble gases almost never become ions because they're full. And since they never react with anything. That's why it's completely safe to breathe in helium. Somewhat safe. It does rob you of oxygen. There's little fear in helium doing anything because it won't react with anything. Conversely, if you do figure out a way of making helium react, it's going to use a lot of energy to make it do that. That's the reason why liquid helium is used in rockets. There is ways and exceptions to force it to react, which enables it to store a tremendous amount of energy. An ion of helium is so reactive because it's extremely difficult to actually make an ion of helium to strip those electrons off because it's already stable, that it will react to almost anything in order to become stable. So this is what I was saying over here. Any side that has 2 electrons is a pair. Oh, I get you for helium. I mean, I've told you to put it on opposite sides. I would accept 0 or 1, because helium is an exception there. No, it would be 0. According to my rule, you put it on opposite sides, so it's, or you put it on unique sides. Either way, helium is an exception. But imagine it as electrons. They're both negative and they repel each other. So you want to get as far away as possible. Technically for oxygen, that would mean this would be probably preferred. But it doesn't really matter because I always draw it like this. Mostly I draw it like this because I know water looks like this. So when you put hydrogen next to it, Hydrogen really wants one additional electron. Oxygen really wants two. So you see that this electron and this electron are shared between them. And it becomes stable. I will say another thing, another exception I forgot is hydrogen. So hydrogen has one valence electron. Now remember, hydrogen and helium are exceptions. They only have one orbital, one energy level, and that's 1s. How many electrons are needed to fill up 1s? 2. So it either wants to get 0 or it wants to get 2. So that means it can either become H negative or H plus. It can either gain, I wrote this on the wrong side. It can either lose 1 or gain 1. So helium is either plus 1 or minus 1. Yes. 0. So this has 0 pairs. So it'd be like carbon, and so it has 0 pairs. So here's water. Its shape looks like this. But if you actually can visualize the electrons are offset. Again, they try to be as far away from each other as possible. But that's actually the shape of a water molecule. There are 2 electron pairs hidden in there. And they're actually at odd angles. When I was drawing it earlier, I didn't really indicate how odd the angles were. It's a 3-dimensional object. I mean, if it's just 3 around it, it could. So that's it for the video. I can't think of anything else to add.